This video is to go over how to balance chemical equations so that the number of elements on each side of the equation are equal. In other words, the carbons on this side have to be exactly equal to the carbons of this side. Oxygens on both sides must be equal, and hydrogens. Now, when you're balancing equations, you can only use coefficients in order to balance the equations so that the left and the right sides are equal of the arrow. Think of it as a math equation, reactants and products. You cannot change subscripts in order to balance an equation. The subscripts are in a compound because of the fact that they have been bonded, the elements or polyatomics have been bonded in a way that is the most stable so that all the electrons are balanced. So please don't ever take the subscripts from the left to the right or start messing with subscripts when you're balancing an equation. All right, so let's look at the first equation. We've got a hydrocarbon plus oxygen that's in a combustion reaction to create water and carbon dioxide. Okay, so in this reaction, you have, I would make a table, and you can put on the left side of the table either the element or the individual polyatomics, depending on what it is. In this case, you're just going to use the elements. On the left side, you have carbons, hydrogens, and oxygens, and on the right side, you have carbons, hydrogens, and oxygens. On the left-hand side, if you add up your subscript of carbons, it tells you that there's 6. On this side, you only have 1. On the left, you have 6 hydrogens, and on the right side, you just have 2. On the left, you have 2 oxygens, and on the right, you have 3. So these numbers need to be equal when you're all done with balancing. So the first thing you might want to do is say, well, let me go ahead and get these carbons equal. So in order to make 6 carbons, I have to put a 6 coefficient in front of the carbon dioxide. I can't change the subscript. When I do that, the carbons are balanced, but now I've changed the number of oxygens. So we have 6 oxygens here plus 1 more here. That makes 13 oxygens. I didn't change my hydrogens at that time. So now if I wanted to fix my hydrogens, I have 6 hydrogens on this side, but only 2 on this side. I can put a 3 in front of the water, and 3 times 2 will give me 6 hydrogens, so I'm good there. My carbons were equal from before, so I'm good, but it changed my oxygens. So now I have 3 oxygens plus 12 more, made 15 oxygens on the right, but I only have 2 on the left. Now, whenever you have an odd number on one side and an even number on the other side of the reaction, usually that means that you need to start doubling your coefficients in order to balance so that you can have an equal amount on both sides. So I'm going to take my coefficient that I had before, and I had a 1 before, I'm going to double it to 2. I had a 1 before, I'm going to double it to 2. I had a 3, I'm going to double that to 6. I have a 6, I'm going to double it to 12. And that's going to make it so that there's not going to be an odd on one side and an even on the other. Now, when I did that, that changed everything. So let's look at my carbons on the left. There's 12, 2 times 6. Carbons on the right, 12. Hydrogens on the left are 12. Hydrogens on the right are 12. So by doubling it, I shouldn't have messed up anything that I had already fixed because I just simply doubled it. So even though the numbers are different, at least they're equal to each other. And so then now I have 4 oxygens on the left, but that can easily be fixed by changing this number, so that's not really an issue. But on the right side, I have 6 here, and then I have 24 more here, so I have 30. So is there a number that you can multiply by 2 to get 30? Well, yes, you can just use 15. 15 oxygens multiplied by 2 will give me 30 oxygens altogether. All of the other elements balanced, and so when you're all done, you would have a 2 here, a 15 here, a 6 here, and a 12 here, and that would be a balanced reaction. The reaction will not take place unless there's enough combinations of each of these compounds in order to balance. Okay, so let's look at the next one. The next one on this worksheet actually comes from Cavalcade Publishing. It's online, so feel free to look that up. Okay, the next one is sodium iodide and lead sulfate, producing lead iodide and sodium sulfate. That's a double replacement reaction. And so when you're doing these kinds of reaction, if you notice that the polyatomic remains the same polyatomic on the left and on the right, you can treat it as one thing. Instead of looking at the sulfur and the oxygen separately, you can just look at the sulfate ion all together. So when you're listing in your table the different elements, you can list sodium, iodine, lead, and then the whole sulfate ion because it stays the same. Okay, now when you're balancing, you probably want to pick the most complicated thing first and start balancing the others to match that, and then you can go forward and balance the simpler ones. So this looks like the most complicated, so let's go ahead and look at it. Lead has one of them on the left and one of them on the right, so lead is already taken care of. We don't have to worry about that. And then sulfate has two over here and one over there. So the easiest thing to do to balance the sulfate is to just put a 2 in front of the sodium sulfate. Now that's going to take care of your sulfates, but it messes up your sodiums. So 2 times 2 makes 4 sodiums. So if I wanted to balance my sodiums, I would put a 4 in front of this. When I put a 4 there, I get 4 of each sodium and iodines on the left. So now my sodiums are balanced, my iodines are balanced, my leads are balanced, and my sulfates are balanced. Let's look at the next problem. Ammonia plus oxygen makes nitrogen monoxide and water. And so we're going to look at this one. Again, we have nitrogen, hydrogen, and oxygen. There's no polyatomics that stay the same. So we go ahead and write our chart, our table here. There's 1 on the left, 1 on the right. That takes care of that. There's 3 on the left and 2 on the right. There's an odd even disagreement here. So typically that means that you're going to have to double your coefficients. And then your oxygens are balanced because there's 1 here and 1 here. So looking at that, let's look at hydrogen. We want to make our hydrogens even on the left and even on the right. So if I multiply ammonia times 2, I get 2 times 3. That would give me 6 hydrogens. But since there's already a 2 down here, I'd have to multiply this times a 3 to get 6 hydrogens on the right. So that's what I would do there. Now when I do that, my nitrogens change and my oxygens changed. So let's start by fixing our nitrogens first. Again, you can go in any order. You could have started with your oxygen if you wanted to, or your nitrogen or your hydrogen. It's just going to be trial and error. You're going to have to kind of revisit. You might have to use a pencil so you can do it again and again and again. All right, so if I wanted to fix my nitrogens now, I have 2 nitrogens on the left, so I would put a 2 on the right in front of nitrogen so that it would have 2. That's going to change my oxygens. I have 2 here plus 3 here, which is 5 oxygens. And then I only have 2, but I can fix anything with the oxygen I want to as long as it's an even number. The problem is it's an odd number. So now I'm going to double all my coefficients that I already had and then look and see what I would need here in order to balance. So when I double, everything else that was balanced stayed balanced. It's just doubled. And then now I can look at my oxygens. Here I have 4 oxygens and 6 oxygen, which makes 10 altogether. If I wanted to have 10 on this side, I would have to put a 5 in front of this. Now, when you look at it, all of the elements are balanced, even though they're in different combinations. I wanted to demonstrate to you another way of looking at this. If you wanted to look at it in terms of blocks, for example, iron hydroxide, number 4, iron hydroxide, this is the compound for iron 3 hydroxide. You have 1 iron and then a hydroxide, and a hydroxide in this compound. And it breaks up into iron 3 oxide. Okay, so you have 2 irons and 3 oxygens in it. I'm calling it iron 3 oxide because the oxidation number in both of these compounds is a positive 3. And so that's why it's called iron 3. And then it also makes water. Now, when you look at the left, you have 1 iron over here, but 2 irons over here. Now, when I put that 2 in front of the iron 3 oxide, I'm basically saying I need 2 of these. Well, that helps me because now I have 2 green blocks and 2 green blocks. But my red and yellow blocks are not balanced. So my yellow, I have 6 yellows over here and 4 over there. I have 6 reds over here and I only have 2 over there. So let's start adding some of these. If I fixed my red ones first, I could make 6 reds, and I have 6 reds, right? And let's look at our yellows to see if they balance. There's 3 and 3 makes 6 yellows. 3 and 3 makes 6. 3 and 3 make 3 6 reds, and 2, 4, 6 makes 6 reds. Now, what this would look like on your reaction is, how many of these did you need? You needed 2 of these, you made 1 of these, and you made 3 of these. And when you do that, and you go back and look at your chart, that's going to balance. So let's look at another example. Nitric acid and magnesium hydroxide are going to combine to form water and magnesium nitrate. And again, the blocks on the left and the blocks on the right have to be the same, but you can't just randomly throw in a block. They have to be in these combinations. Notice here that I kept my nitrate ion together because it's easier to balance. The NO3 and the NO3 stay together. So when I look, the most complicated one here is maybe this one. So I want to have my nitrates over here and my nitrates over here balanced. That means I'm going to have to add something with the nitrate in. I can't just add a nitrate all by himself. I have to balance the reaction. So now I have 2 nitrates and 2 nitrates. So those are balanced. I have 1 magnesium, 1 magnesium. Those are balanced. I have 2 greens and 2 greens. Those are balanced. Actually, 4 greens over here. So I'm going to need another one of these. So if you look, your orange is balanced. Your 4 greens are balanced. Your 2 yellows are balanced. And that would be the same as if you wrote a 2 here, 2 nitrates, 1 of these, nitric acids, 2 waters, and I just made 1 of those. And so that's what in real life it would turn out to be. Let's do one more, phosphoric acid, which is H3PO4, and I have sodium bromide, and I'm going to make hydrobromic acid and sodium phosphate. Again, I used my phosphate ion as a whole thing, so I have a phosphate here and a phosphate there. There's only 1 of each. That makes it kind of nice. There's 1 green, so that's kind of nice. But look, our sodiums don't balance out. So if I wanted to make my sodiums balance out, all right, so I say, okay, I'm going to need 3 blue blocks because there's 3. Well, that messes up my green, so that means I'm going to have to change some of my green blocks. So I have 3 blue, 3 blue, 3 green, 3 green, 3 white, 3 white, 1 tan, and 1 tan. So when you wrote this out, you would only need 1 of these, but you would need 3 of these. You would make 3 of these, and you would only make 1 of those. And so a balanced reaction would look like that. Now I want you to freeze this screen and practice these, and I will show you the answers. Check your answers.